So, hi everyone, my name is Yuri Bogomolov and I will be your host today for today's workshop. This workshop is called Building Embedded DSLs in Functional TypeScript, and we will talk about several approaches how to do this. For those who are watching this in a live stream, there is a comments section, live chat, and I will be showing it right here. So if you have any questions, please leave them in chat. I will be switching to chat from time to time after each section and answer your questions which you will leave there. Okay, so I will give now an overview of the structure of this workshop, and without further ado, let's get started. So the structure would be the following. First of all, I will give a short introduction. What is eDSL in general? So what is DSL and what is embedded DSL? After that, I will give a short introduction to Free-monads. I won't be doing any deep diving into category theory here, so I want this workshop to be 100% practical. So we will just be concentrating on the practical usage of Free-monads. After that, we will switch to code session. And I will show you how to encode your DSL in Free-monads, and we will write some examples. After that, I will do a short Q&A. Oh, by the way, I forgot to add, if you want to watch this workshop in Russian, there's a previous recording of this workshop. It will be available, I guess, somewhere in the description, and there will be also a link in the corner of this video. After that, after the first section, we will have a break, something around 15 minutes, so you can just exhale and rest a bit. And after that, we will switch to the second topic, which is tagless final encoding, or tagless final pattern, if you want. I will do a short introduction what it is, and that we will switch to code session, where we will implement exactly the same API as we did in Free-monads, but in tagless final encoding, and we will encode some examples in it. After that, we will be doing some Q&A. And then we will compare two approaches. So at the end of this workshop, you will have two techniques up your sleeve, which will probably be useful in different scenarios. And then some final thoughts and wrap up, maybe some general Q&A, some chat interaction, something like that. So let's get started about the first section. What is embedded DSLs? In general, what is a DSL? Just a second. So what is DSL? DSL in general is an abbreviation of a domain-specific language, which is some kind of computer language which is specialized to particular application domain. An example could be, for example, SQL, structured query language, which deals with only one domain, is querying the relational database. So, for example, in pure SQL, you cannot, encode a network request, or you cannot write ray tracing engine in SQL, but you can effectively use it to describe relational algebra. So, the domain of that language is relational databases. In contrast, embedded DSL is a subset of your host language, which deals with this task of specializing work in some application domain. So you can think about it as some kind of API which is strictly limited to that business domain. Let's take a look at some examples. The first one should be familiar to, I guess, many front-end developers. It's JSX from React. So you are writing something which looks like JavaScript, but it's actually have HTML embedded in it, and it's either an example of DSL, which describes business domain of components. Another example of purely eDSL is Nex. Nex is a library for writing database queries, for generating SQL. So you can think of it as a library with a rich API, which allows you to express SQL queries in something that looks like JavaScript or TypeScript if you use, for example, TypeORM. Basically, you are using your host language. You do not write queries in SQL, but you are using JavaScript to change some methods, and at the end you run some system method which will give you completely generated valid SQL query, which is the thing that you actually want. Another example would be the do syntax or do notation, which I will be using today for expressing the examples. This is an emulation of do notation from Haskell for FPTS library. So you can express your monadic actions in a plain, simple way. You build some context and then you call the return method, which will unwrap that context and do actual computations. So in general, the idea of DSLs or eDSLs is that you build some expressions and then you evaluate them to the target language, to the target system or something like that. So the main idea which we'll be focusing on today is separating the building of expressions to their interpretation. And the first approach we will be looking at today is free monads. So what is a free monad? Basically, there's a concept of a free object, free construction, and we will be talking about free monads today. So free monads give you a monad for any functor. For example, if you have a data type for which you can define a functor, you can lift that functor to a monad for free. The basic idea is that you encode your monadic actions in some kind of data structure, and you do not do the immediate evaluation. You just describe actions and do not execute them. And it happens so that free monads are a great way of building an embedded DSLs. So we'll be looking at them at the practical application today. You can remember this concept that free means free of evaluation, free as in freedom, and not in free beer. So maybe this will help you. Okay, so let's switch to code session now. In the description of this video, there's a link to the repository, which I highly encourage you to clone to your computer and check out the master branch, which is the default. Because with this template, it would be much easier to follow this workshop. So let's talk a little bit about our application domain, which we'll be describing today. So we are writing something like blogging platform, and we have these two entities in this workshop, which are called user and post. So user is just a collection of ID, name, and email. Post is something which has title, body, tags as an array of strings, and a reference to the author of this post. For convenience, I gave a few type aliases. For example, db post is a post which is persisted to the database, and thus it has ID as number. Another one is a little bit trickier. It's called post update. So when we will be describing an update operation for post, we want it to have author and at least one of its fields. So you cannot update a post with only author. That's not a valid operation. But you can update a post if you have at least title or body or tags or any combination of them. This type operator, maybe at least one, is defined in a folder called utils, so you can take a look how it's implemented. And for example, I gave two entities in our business domain is a user called John and a cool post which is persisted to database post with a title, body, empty tags, and it belongs to John. In our business domain, we have three ways of interacting with the outside world. First one is key value storage. So you can think about it like something like Redis or KeyDB or Memcached or maybe, I don't know, local storage for browser, you name it. And the second one will be some kind of relational database, which will be our persistent storage. So Postgres, MySQL, I don't know, something like that. So the main work will be done in a folder workshop, and the first section is Free-monads. So the first module which we'll be writing is called API.ts, and in it we will encode 7 operations to interact with our entities in the business domain. So for key value store, we will implement 3 operations: kv get, kv put, kv delete. And for relational database, we will implement a little bit more higher abstracted methods. One of them we will get posts, an array of posts for given user ID. The second one will create a post in the database, and the third one will update the post in the database. And the last one operation is encodes an interaction with network. So for any payload which is abstracted with this type parameter t, you can send that payload to a given email. and the result is just void, so this operation won't be returning anything, but it will do some side effects. Our API will consist of 7 methods which will encode those operations, and for now they are just stopped with not implemented function, which just throws an exception saying that this method is not implemented. So let's talk about free monads. I will split my window vertically so I can see the description of the operation I'm encoding. So as I said before, free monads means that we are merely describe an operation and not execute it. So for encoding the kvget operation, we need some way of encoding a function with one parameter, key of type string, and return type of option. And this should be just plain value. It should not do the actual computation. And it is done like that. I'm creating a class. I will call it just like this operation, kvget. This class will have a field called tag, which will be of type string literal kvget, and its value will be the same kvget. This tag is required to separate this class from the others in runtime. This class will have a constructor which will hold fields for encoding this operation. So our first field will be key of type string, and the second, the last one, would be a field which should encode the meaning of return type of the function of type option of string. And by the way, I need option, and option I will import from a library called fpts. Import. I will import it as module from fpts lib option, and then I will write type import synonym import option equals r.option. So to encode this part of function, I'm intentionally selecting the arrow to show that we are encoding the return type of function. We will do something called continuation. So we will add a function called next. Its parameter would be value of type option of string, and its return type will be something called continuation, which will be a type parameter to our class kvget. So like this, we will encode all the operations. So the encoding is the following. For each function, you have a set of fields in your class which represent the parameters of that function, and you have a continuation function next, which takes an argument of type of return type of the operation you're encoding and returns some generic type continuation. Let's describe like this an operation kv put. By the way, this is not the final definition of that class. We will need 2 extra fields in each of that classes, but I will get to that at the end when we will describe all the operations, because those classes need to be something called higher kinded types, and I will explain why a little bit later. So meanwhile, let's describe all the rest of the operations. Kv put is a generic in continuation. It has a tag, return with tag, type is kvput, and the value is kvput. Constructor. The constructor return with key of type string, return with value of type string, and return with next of type, I will call it is okay, of type boolean, and it will return continuation. And the last one for that set of operations is kv delete. Continuation is a type parameter. Tag is kv delete. And the constructor will have parameters key of type string, and next as a function is okay, boolean to continuation. Yeah. And when I'm describing my APIs in Free-monads, I like to group those operations with some types. So I will have kv store f of continuation, which will be just a some type of kv get, kv put, kv delete. All of them are accepting that continuation parameter. Please note that I'm not exporting those classes to public. In general, you don't want those containers, those classes, to be available in public, because your public API for that module will be just those functions. You don't want to give public access to the internals of your Free-monadic API. That's just how encapsulation works, I guess. Let's continue. We're now describing database operations. So the pattern is exactly the same. I will create a class called get. I will call it db get posts, which has the same type parameter called continuation. It has a tag. It has a constructor which has first parameter is user ID of type number, and the return type of that function is encoded with a next function which accepts a list of posts. It's db post array, and it returns continuation. I need to import db post from module domain db post. Yeah. Next, class db create post, parameterized by continuation, has a tag, and it has a constructor. Return with post is post. Return with next as new post of type db post, and returns continuation. And the final one is class db update post. Return with tag db update post. Constructor. It has two parameters, so it has parameter called post ID of type number, update of type post update, and the return type is encoded as a function next with updated post of type option of db post, and it returns continuation. And I will group them together with data type database f of continuation, db get posts, db create post, and db update post. Those type aliases in general are not required. I'm just doing them for convenience, so we can see which parts are grouped together logically. And the final one class is network operation called netSend. NetSend of continuation. Only tag netSend. Constructor. Read-only payload. And this one is a little bit tricky because you see that netSend operation is polymorphic in its type of payload, so it has type parameter. In order to do that, we need to add another type parameter to the class, because in TypeScript we can't make constructor polymorphic without having the main class polymorphic in that type. So we add payload. We have email of type string, and we have a function next, which doesn't accept anything and returns continuation. And finally, we export type program f of continuation, which will be a sum type of kv store f of continuation, database f of continuation, and netSend of continuation. And you see that netSend requires two type arguments, and we in general want our Free-monadic APIs to have one type argument, the type of continuation. So I will just plug an unknown here, because in general I don't care which type of payload I will be getting, and in my public API I can work around that. But that's not all. In order to make usage of those classes, we need to lift them to a Free-monadic context. So in order to do that, I'm importing a function called liftf from a module called fpts contrib, not just fpts, but fpts contrib library, lib free. Before the release of FPTS version 2.0, Free-monads were a part of its API, but in the second version of this library, they were moved separately. Actually, they were abandoned, and I've contacted the author of this awesome library, Giulio Conti, and asked that I would like to get free back, and he suggested me to move them to fpts contrib module, so which I exactly did. So we need this function liftf in order to lift our encoding to the Free-monad. How is this done? For example, we will encode the function, I'm sorry, not encode, but we will describe the function cache getPosts. Its body is just a call to liftf, and you see liftf requires a type called hkt, higher kinded type of something unknown. And I want to write it like this, kv get, and pass user ID interpolated as a string to kvget and pass something to a function next. But I cannot do that because kvget is not a higher kind of type, and in order to work around that I need to add 2 more fields to that class and all the rest of the classes, but those fields will be the same for each class, so that's not a problem. In general, I want my type program f to be a higher kind of type. This means that I need to be able to pass that program f to a things like functor or monad, or in this case Free-monad. And in FPTS there's a pattern for that. It's based on a really cool paper called lightweight higher kind polymorphism. If I recall correctly, that paper was written in OCaml, but it was translated to TypeScript, and in order to convince the compiler that our program f is a higher kind of type, we do this. We write declare module fpts/lib/hkt. There we write an interface called URI to kind. It has one type parameter called a, just a, and this would be our continuation actually. And there we write program f is a program f of a. And we want to store that string representation of our type, that string literal, that key program f, as a separate entity. I will write it as a const called program f URI. It has program f type, and I'll have a type called program f URI, just exactly as the constant, and has the same type of program f URI. And those 2 entities I would like to have as a part of my public API of this module, so I'll export them. Now, for the compiler of TypeScript, for the FPTS library, we have this type level synonym, that special type kind of string literal program f, and some other type a is exactly the same as our type program f of a, thanks to this type level mapping. But in order to our not only our type program f, but also its composite parts to be higher kind of types, we need to add to those classes 2 fields which I told you earlier. So the first one is called _a, and it has type of continuation, our type parameter. And because TypeScript will complain that property a has no initializer, and we cannot actually instantiate this type in our constructor because we don't need that type, I will write a bang here, which will convince TypeScript that this is okay. And you see that those 2 fields which I will be adding here, they are required just for the compiler. They don't required in the runtime, and that gives that higher kind of type encoding its effectiveness. And another field which we will need is called URI, and it's of type program f URI. And those 2 fields I will copy and add to each of the classes. So kv put, kv delete, db get posts, db create post, db update post, and net send. After that, the instantiation of that class would conform to the interface of type HKT from FPTS, and everything will be okay. But we need to pass the function next. Next is a function which should be of type which encodes the type of option of string, but we actually want to return an option of db posts here, because for there's a mistake here. It should be actually option of db post array, because for given user ID we might not have posts in the database. So we need to transform an option of string to an option of database post array. Right now I'm encoding a work with a key value storage. This key value storage will have keys as strings and values as strings. So I'm thinking that I will be my post array just stringify and put it in that storage, and in order to get the reverse I need to call JSON parse on that string. But I don't have a string here, I have an option of string, so I need to transform an option of string to an option of db post. And that's possible because an option is a functor, so I'm calling a module option, which I have imported as a synonym o.map. And for that map, I need to pass a function from string to something. And this something right now is inferred as unknown, but it should be db post array. So I need a function from string to db post array. So I have some string, and I will call JSON parse str as db post array. In general, in production code, you should do some more serious validation of that. For this particular example, it's okay, because I know that I will be writing just valid JSON strings to that key value storage, and I will be reading them, and that's okay to cast them as using as keyword. But I beg you, don't use this approach in production. You need to always validate your data. So probably you want something like IOTS library here, but to keep this example short and clear, I will be just pretending that I know what I'm doing. That's okay. And now our code compiles because there's no warnings. Let's take a look at the type of function cacheGetPosts. It's a function of user ID, and it returns something called free of our type program f, and the return type is option of db post array. So this function cacheGetPosts will construct special container which will encode this operation from taking a string and returning db post array. And that's the approach which you want to use when describing a Free-monadic API. You create a container class for each of your operations. You encode your operations as that container class, and you lift it to a Free-monadic context using function liftf. Okay, so let's implement another functions. So liftf cache store posts will call under the hood kvput operation. So we need to construct kvput, an instance of kvput class. It needs key. We have user ID of type number. We will interpolate it as a string. Again, in production, you want your keys and key value storage to be more descriptive, to be more specified, to be easily distinguishable. But for this example, I will just use user ID because nothing else will be stored in this key value storage. And for value, I need another string, and I have an array of posts. Probably I want this to be db posts. So I will call JSON stringify on those posts. And finally, I need to pass a function which will transform is okay boolean to something, and that something I would like to be just the same is okay boolean. So I need a function from boolean to boolean which does nothing, and I have this function. It's called id. It's identity function. It's written like this, but in order to minimize the amount of allocations, I'll just use a function called identity from fpts web function module. So you need to import function identity from fpts web function, and there you have it. Function cache store posts, which takes user ID and array of posts and returns a value representing computation which results in boolean result. Okay, let's write cache invalidation. With f new kv delete string interpolation of user ID, and I don't want to do anything, so I will just pass an identity here. Next one is db get posts. Just the same pattern. With f new db get posts. I have user ID of type number, and here why does it want string? Because I've written it as a string, and actually my operation has user ID of type number, so I've made a mistake. I apologize. And user ID will be just number. So I'm passing a user ID here, and I don't want to transform those posts in any way, so I just pass an identity. Next, db create post is with def new db create post. It has post and it has function of transformation. Again, I don't want to do any transformation. I just pass an identity here. Update post new db update post. It has post ID as number, update as a post update, and next as identity. And finally, I need to send an array of posts over network to some email. So I call with f new net send. Payload would be just posts. Email would be our to variable, and next is a function which takes nothing and should return void as well. And I have that function already defined in fpts web function module. It calls const undefined. So I'm importing that function from module fpts web function. So there you have it. Let's wrap up. In order to define a Free-monadic API which encode those operations, we create container classes for each operation. That class, each class should have a tag so it can be distinguished in the runtime. It has two special fields just for the compiler, which are required in order to make that class a higher kind of type. The constructor class has a set of fields for each parameter of the operation we are encoding, and the next function, which is a continuation, which accepts an argument of the return type of the operation we are encoding and returns the special type continuation, which is a type parameter of that class. For all those classes, you want to define a type, general sum type, which represents a whole set of operations in your business domain. You want to make that type a higher kind of type, so you want to use module augmentation pattern in order to convince the TypeScript compiler and the PTS library that your class could be used with a special type kind, and in our case with a special type free, which accepts that URI and represents actually program F of that URI. And your public API consists of functions which called special function liftF from module fpts contrib/web/free. You instantiate that container class you created earlier with all required parameters. So at this point you are not doing any computations at all. You're just creating structure in memory which represents the computation. So as I told in the introduction, DSL is separated into two parts. The first one is building of expression tree in this particular case, and the second stage is interpreting that expression tree from the first stage into something actionable, into computations. So right now we did a first stage. We created an API which allows us to build the expression tree. Yeah. So I hope everyone was able to follow me. If you joined right now and haven't catch up yet, don't worry, I've created a few recovery points in the repository. So right now we've finished the first recovery points, and it's called 01 Free API. So if you want to continue following from that point, please just check in that branch, and you have just exactly this thing which I've written right now. Okay, so let us continue. We've written our API and we are ready to put it to use. So let's open a file called examples, and here I prepared 3 examples for you. The first one is we will get a list of user posts and we will put them in the cache. So the first step is we will take a look at the cache, and if in the cache there's no post for that given user ID, we will go to the database, fetch those posts, cache them, and send them to review, for example. Very synthetic example, I understand, but I just wanted to use as much of our API as possible. The second example, we will create a post, and then we will fetch top 3 posts and send them to the author's email. And the third one, we will update a post and invalidate the cache for that post, and then we will return it. So let's write that. Oh, by the way, in the module API, we don't need the not implemented function, so we can keep our imports tidy and neat. Okay, so as you probably guessed, here our example program should have a type of free of program F URI, which is imported from API, but actually I want that API to be imported as a module. So we have it like so, api.programFURI. I'm doing this because I just want to be able to call that methods to keep my API discoverable. I'm importing it as a module and using it like this. Okay, so let us write this down. We will describe that flow of actions as a monadic computation. So, as you probably know, monad is an abstraction of a sequence. So you have one operation, then another, and Monads model exactly that. So monadic function bind or chain in FPTS terminology does exactly that. It takes an unwrapped value and returns a new computation, new monadic type. And in order to work with those chains more easily, there's a thing called do notation, which I showed you in the presentation briefly, and we will use it now. So the do notation is available in module fpts contrib /lib/do. And we will need to import just one thing, is a class called do. The usage is the following. First of all, we need to call it and give it an instance of a monad we are going to work in. So our monad is a free. So for a type free, there's a separate instance of a monad called free lowercase, which is available in the same module fpts contrib lib free. So I'm just importing that free lowercase, and I'm passing it to do. After that, I have a few methods which I will be using. So the do itself is an example of eDSL, as I told in the presentation. So its domain is monadic actions. So I have a few ways of combining them, using bind, using do, using let, using sequence. And when I'm happy with that, I can call either done method or return method in order to unwrap that syntax tree into exactly required monadic computations. So we will start with a code of bind. If you haven't used the do notation to this point, you can think of it as something which builds up a context. So each method, bind, in the chain bind, bind L, do L, sequence, let, adds something to the context. So you can think that each method chain builds another expression in some context in the memory, and in the callbacks of each method you have an access to that context, and you can extract all previous values which you've built and build something based on that. So we need to start with something, and its something would be a thing called cached posts. So I'm hoping that posts exist in my key value storage. So I'm adding to the context a variable called cached posts, and it would be obtained via called api.cache get posts for a given user ID. Next, I will use bind L methods. L called lazy because it accepts as a second parameter a callback which has an access to the previously built context. So next, I would like to have an array of posts which would be either obtained from the key value storage or obtained from the database and cached. So this will be quite big function, and it has an access to the context, and from that context I will extract cached posts. Please pay attention that cached posts is an option of db posts. It's not a free of something, and our cache get posts returns free of this exactly type. So you can think that method bind L unwraps previous computation, takes something, and it should return another monadic action. So I'm taking that cached posts, and now I need to look inside that option, and if posts are present, I need to return them as is, and if posts are absent, I need to go to the database and then store them in the cache. For that, I need I need to work with an option, with a container option, and for that I need to import a method called pipe from FPTS with pipeable, because I want to write right now idiomatic FPTS code, so I will use pipeable methods, and I will replace this named import with a module called O, and I will add an import synonym as previously done, O.option. So I need to call pipe. It accepts cached posts, and then I need to do something with that post, and I would like to dive deep into option, and this could be done with a method called fold. Fold accepts two callbacks, one for none case and the other one for some case. So here we have posts, and in first part we don't have posts in our cache. So if we have posts in our cache, we just need to short circuit and return them. But each method in bind should return a free monad, and I have just db post array, and I need to wrap them in a free. So in order to do that, I call free dot off. Off is the monadic method which wraps the value of type something into a monad of that something. What I'm writing posts, free of posts. And in first place, I need to right now I need to make a call to the database. So I need to call api.db get posts for that user ID. But after that, I want that post from the database to be put in the cache. I don't want them to just be returned and make this trip each time. So in order to do that, I need here to make another free-monadic computation. I could use this do syntax, but I have just two computations, so I will just use the method chain directly, free.chain. That method takes first argument as db get posts, and the second argument callback should store those posts in cache, and that method returns just boolean, and I need to return those posts. So I will use free.map, because free is a functor, API cache store posts for user ID those posts, and I will return those posts. Okay, finally I have the next computation. I need to send those posts to review. So I use another bind L, another function which has an access to the context. I have cache posts and posts. I don't need cache posts anymore, so I'll just take posts from that, and I will call API net send posts to review at example.com. And finally, I need to unwrap that context which we were building in do notation, and I will call return method, which has an access to the context. From that context, I will take the result of that network call. It's just an undefined, and that undefined I will be returning. Actually, I could just plug here the function const undefined, but I like to keep it this way, because if in the future my API will change, and for example my net send post will return some type of result of the network call, this approach will preserve that result. And so yeah, as you can see, the code compiles now, so TypeScript doesn't complain anymore, and we have our first example. So let's take a look what happens here. First of all, we are starting with a trip to cache. We are trying to get posts for given user ID. Then we have an option of post array, and we are taking a look using float method inside that option. If we have those posts, we are just short circuiting and returning them as is. And if we don't have those posts, we are making a trip to the database using dbGetPosts method, and then we are storing those posts in the cache, and we are using functor to transform that boolean into dbPost array, because we need that operation to return an array of posts as its final result. After that, we have our array of posts in our context, so we are just taking them out and making a network call, just sending those posts to review. And finally, we are unwrapping our do context and returning that network call result. I won't be writing these next two examples. I encourage you to write them by yourself, probably after this workshop, so we can just spare some time. But please write them by yourself. Take a look how Free-monadic APIs are used. Probably if you want, you can abandon do notation and use just a sequence of chains. You can use free with a pipe, of course. So just experiment a bit. And this concludes the part of usage, our Free-monadic APIs. So if you joined right now or haven't catch up to me, you can check out the branch called free example, which has all three examples done. So it won't be as interesting for you, but if you want to, I don't know, maybe check your implementations with mine, so you can check out that branch as well. And of course, that branch has all previous work done too. So we've covered the first part of building eDSL, creating an expression tree, and using it, creating an API for building expression trees, and using that API to actually build an expression tree. And this program is not a computation. If you run this code and you, I don't know, call that example program as a function, you won't be getting anything. You won't be getting any network calls or something like that, because you're just building a tree in memory, and that's all. In order to transform the tree into actual work, we need something called interpreters. And for that, we have a file called interpreters ts, which is empty right now, except for that comment. So we will be writing interpreters for our Free-monadic API. In order to make this interesting, I will be transforming my free monad into concrete monad called task. Task is a monad which is basically a lazy promise. So if you didn't know, the promise in JavaScript is not a monad, although it may appear so, but promises are eager and they do not conform to monadic interface. there was an unfortunate event when guys who really knew computer science and knew how to design programming languages asked the author of Promise a star proposal to please make promises monads, make method to construct promises code of, make then call callback take only one parameter, which will be a monadic action, and make catch be as is. But the author said that there's no practical usage to that. That's just some academic nonsense and gibberish, and we have promises like they are now. They are not monads, and yeah, it's a little bit of sad story. But it happens so that if we transform promises to the lazy side, if we just make a function that returns that has no arguments and returns a promise, it happens so that this type could have monad interface, it could have a functor interface, it could have applicative interface, and finally it can have a monad interface. So we will be using it for our interpreters, because I want to emulate real work with a database, real work with network, real work with key value storage. And you don't need to write that type or instances for functor, applicative, monad by yourself, because you have this type in FPTS library, which is cool. So we will have it like so. Export. I will create a function which will return me an interpreter. This will be a function which will here return something. I'm sorry, it's return. Yeah, and I need to explain you one more thing. When we are talking about free monads, the interpreters is something which transforms free of some URI and some type into another type. Here it will be f, into another type of that parameter. So in the context of free monads, interpreters is something called natural transformation. And natural transformation is something which for all types A transform f, let me have it that way, f of A into g of A. In TypeScript it would be written like that, type interpreter. So my interpreter would be transforming into tasks, so it will be like that for all A. And as we know, for all means just abstracting the type argument. For all A given given what? Given program f, not just free. Given I've made a mistake here. Natural transformation is something like that. So we have some program of type program f, which will we will import from our API, and we will have program f of A. We will transform that into task of A, and task we will import from FPTS, as I told previously. Import, and I will do this as module from FPTS with task, and import task is t.task. So type interpreter is natural transformation from program f into task. and we will use this type of function with another function from module 3 called float free, which we will use in order to transform our free-monadic expression tree into actual computations. So this function returns me an interpreter, and an interpreter is a function that takes a program of type program f and returns a task. I'm sorry. So how can we create a task from that program? Because, as you recall, program f is just a giant type sum type of 7 possible combinations, and for that we have that tag in each class which allows us to distinguish those classes one from each other. So I will be writing a switch statement for program.tag, and I will take a look inside each case. So for example, let's start with kv get. kv get should return me a task. I need to have some way to talk to a cache. In this example, in this workshop, I won't be bringing into scope some libraries to work with Redis or with memcached. I won't be bringing into scope something to work with Postgres. I will be just mocking that behavior right here. Of course, in your production cases, you would write an actual code that you will be writing exactly the code which will talk to Redis or Postgres or some other your systems. But I want this to be short and clear, so I won't be doing that. And I will have my cache just as a map, JavaScript map from string to string. Map. Okay, so I need some way to translate that kv get structure into actual computations, and those computations would be this. I will create a task I need to pass a type of A, and this A, as you recall, it's unknown, it's a polymorphic type, it could be anything. And I have just a method for that job. It's called program.next. So that type A is actually a type of continuation which we were using in those classes. So I need to call that program next and return it a value of type option of string, which we can obtain from our cache by using the parameters which are available in the program variable. So I need to construct an option, so I'm importing module option from a PTS, and option has this awesome method called from nullable, which accepts a nullable type and transforms it into an option, and that would be just my cache dot get. I need to get a key, and I have this key in program.key. So yeah, I guess that should do. So let's check task. I have a task of A, next has type A from nullable, gives me an option of string, just exactly what I wanted. Probably I will, if I remove this type, yeah. I need to specify it anyway. Okay, so now let's write another switch case for kv put. So we need to store something in cache. How we will do that? We will turn task of program.next, and we need to return OK, and this could be done, for example, like that: cache set program key program value. It returns me cache. I will just test that it's not null. Finally, kv delete the same thing. Program next is okay. I have just exactly API that I want because delete method returns a boolean. Program.key. So we've interpreted the first part of our Free-monadic API, which is related to work with cache or key value storage. Next, we need to describe how we are interpreting work with a database. For database, I will have another mock. I will call it db_fake. It will be of type db. I have in my utils module utils/db type db. Let's take a look at it. It's just a record of user ID and another record of db post ID and db post. So actually, I'm modeling my database as two hash tables. One outer one holds user IDs, and the inner one holds post IDs. And the values are actually that map and that post. And I have written a convenience method to get the next ID, which we will use when we will interpret the create post method. So, okay, let's move on. I'm creating a task from program.next. I need to get an array of posts. I can get them by using object.values. Right now, I will define it later. Object.values. I need to have a hash table of my posts for given user ID. I called db_fake program user ID. I need to probably fill my database with some examples. I have a user called John in my domain. John has some ID. John will have a cool post ID, cool post in that database. Yeah, awesome. Next, db create post. Turn t off. Maybe not. First of all, I need to create a new post. So I have at my disposal, I have program.post, which is just a simple post without ID, and I need to have ID for that post. So ID would be get next ID, which is imported from utils/db. For that, db_fake and author ID, I have it in program post author.id. My new post would be just an object with a spread of program.post and this generated ID. So new post will have a type of db_post. Finally, I can mutate my db_fake from program.post author.id. Probably I need to ensure that there's a hash table for that, and then I can assign by ID that new post. And after that, I return task of program next of db post, which is my new post. I should say that this local mutation is okay now. In general, I prefer to write purely functional code without any mutations, because mutations are something you really want to avoid. But in this case, it's okay because this mutation is limited by the scope of my interpreter, and I have full control of that. And again, this is some toy example. My DB in production would be normal Postgres, which will handle all that stuff, and I will just make a pure function which calls the Postgres and returns the result of the call. Let us continue. Finally, we can update our post, and to do that, we need first of all make a trip to the not make a trip, but take a look at our DB fake and try to get that post by update parameters which are available in program here. If we have that post, we overwrite it. If we don't have, we just short circuit and return nothing. I will import pipe from fpts with pipeable, because I will be working with option right now. So I will return a pipe. This pipe will accept option from nullable, db fake from program.update.author. And by the way, here you can see the type of post update. So it has an author and 3 optional fields, but in reality the TypeScript won't allow me to construct a post update without passing anything. So I will use author ID to get that. I will do a little bit of defensive programming here, and then I will call program.post ID. So I'm trying to get a hash table of author's post, and then I try to get a post by post ID, and I will wrap that in nullable. After that, I want to forward that nullable. If I don't have anything, I just return task of program next of option of post. I don't have anything, so I construct option none from thin air by using none variable. And if I have a post, I will call it existing post. I need to update it. So my updated post would be a spread of existing post and program update. Next, I would like to override that program update author ID by program post ID, and we are writing that updated post there, and then we just return it t of program next. We have updated post. We need to write to wrap it in option. We just used o.sum, which constructs a new option of db post, and we have our updated post here. And here's that. And finally, we can write a final case, net send What's wrong? Oh yeah, I need to write that, and then we will have it done. So I will write t off program next, and probably that's all. For network calls I will just ignore those parameters. So I will pretend that I'm doing some network request and sending something to that email. In reality, you would like to use some kind of fetch API probably, or access, or you name it. But for now, I'm just pretending that I did that and I return a task. To make things more interesting, I will wrap each of those tasks in a delay. So we will emulate real behavior of key value storage and database. So you could see that asynchronous operations, when we are interpreting them, take some time. So I would like for this workshop that the behavior of my program would mimic the real world. So for cache, probably I won't be doing much of a delay, because in reality you want your cache to be as fast as possible. But for database, I will wrap that task into a delay function, and that delay for get post, I don't know, probably let's go with 500 milliseconds. For creating a post, we will delay probably go with something like 300 milliseconds, because probably we need to invalidate some update some indices in database, you know. Then update, because we are looking for post and then updating it and then writing. I guess that delay should be bigger, so delay, I guess 750 milliseconds. And for network, because network is really slow, we will use 1 second, for example. So when we will be running that interpreter, we will see the real delay of those operations. But I'd like you to see that this program is doing something, and if we just run that, it will be tossing some bytes in memory. I will write another interpreter, another natural transformation, which will be just some kind of identity natural transformation, which will turn program F into program F. But it will log, because in JavaScript we don't really control the side effects as granularly as I personally would love. We can just put some console log in there, and yeah, that's it. So I will export something called logger, which will be of type interpreter, and it would be something which will transform my program, return it as is without any oh, I'm sorry, not interpreter transforms program into task, and I would like that to be just identity. So I will write the type explicitly, program f of a, and returns program f of a. And here I will do this little trick. I will use that fact that I can destructure my program. I will take out tag and I will spread the rest. And then I will write a console log statement with the following shape. In square brackets I will write the tag, so we will have a column of operation text. So you can see which sequence of operation is executed, and then I will write JSON stringify of rest. Yeah. So that were our interpreters. So again, let's wrap up. What is an interpreter in the context of free monads? Interpreter is something called natural transformation, which transforms your type of program into some other monad. Well, basically into other functor, but that's not the let's not nitpick. Program, we are not talking about free here, so natural transformation doesn't know anything about free. It knows only about one container and another container and transforms those containers. Our interpreter is just a transformation from program f into a task. A task is a lazy promise, and we are just doing a case split on program tag, and for each class we are interpreting its parameters into something. So as you see, let's return a bit for API. Our classes are just dumb containers. They don't contain any logic, they are just holding the values. So our interpreter uses that program is just a container, extracts values from them, and uses those values as a way to do actual work, do actual calls. So here, as you can see, I'm actually mutating some state, I'm doing some work here. I could use fetch API to do some network calls. And I can write another natural transformation which will transform my program f into program f and do some logging with that. This perhaps the part of interpreters. If you want, if you didn't want to write that manually, you can check in the branch called 03 free interpreters, and for examples, as I told, you can check in the branch 02 free example. Finally, let's run this stuff and see how it behaves in runtime. So we have this run.ts module, which actually just creates an async context, so we can use a wait operator here, and it suggests you to run program 1 twice to see that behavior of cache, and program 2 and 3 are executed just once, but you can write them as many times as you want. Okay, so let's import example 1 from ./examples example program 1, and let's import from interpreters our two functions, get task interpreter and logger. So our final interpreter would be a composition of task interpreter and logger. So we need to have task interpreter, get task interpreter, and our final interpreter would be just flow of logger task I, and flow is a function, is a function from module FPTS lib function. It's just a composition of functions from left to right. So in order to run our example program 1, we need to call this special function from module free, FPTS contrib lib free, and this function is called fold free. So we are calling fault free. It needs to have as a first argument an instance of a monad for that concrete type which you are interpreting into. In our case, this is task, so I'm adding an import of task. fpts lib task, and an instance of a monad for task is called just task. So we are passing that argument to fault free. Next, it has this big data type with the name of NT. NT stands for nature transformation, and we have exactly that. It's called interpreter. So we are passing interpreter here, and finally we need to pass that free of something, and we have that free by calling example program 1, and we need to pass user ID, and we will use our trustworthy John with its ID. Then we will have a task of void. As a result, we need to run that task in order to get promise, and that promise could be just awaited. And I will copy that execution line once again. So we can see that stateful interpreter actually live. I will comment out that those two examples, so I won't have any runtime errors due to not implemented, because that function just throws an error and I don't want that. So I'm opening a console, and you can run your examples by using script from package JSON called run fm, run Free-monads. So I'm doing just that, npm run fm. It's running TS node that right now, and let's look closely at the results. In first run, we are going we are going into cache. We don't find anything, so we go to the database with our user ID, and then we cache those posts in our cache and sending them. But in the second run, we are going to cache. We are finding those cache because our interpreter is stateful, and we're just sending them. So in second run, we are not doing a database round trip. So this is some kind of optimization. And as you probably saw, if I run that one more time, it's written to the console with some delay because my interpreter has those delays put into the its implementation to emulate that behavior. What's really cool about all those eDSL approaches, especially in those two approaches which I'm talking about today, you can abstract your effect. For example, you can abstract the effect of asynchrony from your business logic. So if we take a look at that example, we are not talking at all about asynchrony. We don't need to know that this example program could be running in an asynchronous context. It could as easily be running in a sync context. And I did exactly that in tests. So you can open your console, you can run npm test, and it will run some tests for free and tagless final. Right now the test will fail because I haven't implemented second and third example, and I haven't implemented tagless final. But my I'm sorry, my examples should work. well, at least example 1 should work flawlessly. I've written another interpreter which interprets my program F into a state of some kind of test state. So I can introspect the results of that execution in a purely functional way without talking about promises at all. My tests here are purely synchronous. They don't know anything about promises. So my state interpreter is just a natural transformation from program F into state of test state. I'm just doing the same. I'm case splitting on program tag and returning the next state and the result of execution in a synchronous manner. So I have just think about that. I have the following behavior. One business logic written only once. That business logic is running in asynchronous mode in production. That the same business logic is running in synchronous mode in tests without taking any changing any line. So I'm just writing different interpreters with different behavior and running and using them to run my business logic. So I can expose that Free-monadic API to public, and my programs which will consume my API, they will use that Free-monad DSL to express those programs just as we did here, and they can interpret them in different way. They can have their tests running quickly, and they can have their production implementation run in asynchronous mode against the real databases. So again, they here in tests, I'm just creating a mock of database and cache. I don't need in tests. I don't need to set up big program state with some fake database, fake cache. I don't need to mock modules which talk to network in order to intercept those calls and then use just mocks and all this machinery. I'm just using plain simple out state. That's all. So I hope you can see that this approach is really good testable. So yeah, the results are in the branch free interpreters. If you have any questions, I'm glad to answer them. So first of all, guys on a call with me. Sorry, can you please rephrase that? I didn't get the question. Oh. I guess, well, I don't remember the particular reason why free was taken out of FPTS version 2.0, but I believe from GitHub issues that Julio was rewriting that FPTS version 1 from classes to just plain interfaces, so the library would be much more performant and easier and more idiomatic to use, but the free encoding still requires those classes, just like we did in our API. Internally, free monads have two classes called pure and impure, and that those classes have these fields, well, next and URI, and they were just impossible to rewrite in the same way that Julia wanted the core of PTS to be. I believe that was the case, so he just deleted them, and I asked him to return them, and we decided to just move them to ifpts contrib module. Okay, sorry, in chat they asked to repeat the question. Probably the sound from Skype is not translated to YouTube for some reason. That's strange, but that's strange. Okay, so the question was how to explain why do we need this to be so complicated to our teammates. And the previous question was the reasons why free as a module was taken out of FPTS. So the question of explaining this to others is, I should say it's rather complicated, because obviously this approach is not an easy, because you need to know some really advanced stuff. Probably Tagless Final would be easier to explain, as we will see in the next section. It would take less time, but Free-monads give you a whole different level of capabilities when you are writing your APIs like that. For example, programs in free-monadic style could be introspected and, for example, optimized. So if you see that you have, for example, one branch which holds another branch, you can combine them together into into one, for example. Actually, when you are building an expression using Free-monads, you are building some kind of AST, abstract syntax tree. And as with any AST, you can transform them. You can do different kinds of cool stuff. And from my perspective, if you don't need that, probably you should go with simpler approaches. But Free-monads give you basically that. They give you a way to build an expression tree and do something with that. So if you, for example, you can interpret that that AST into different effects, into the different monads. You can serialize that expression tree and transfer it over the network and execute, reinterpret and execute it on the another node. So, for example, if you're writing some distributed software which requires some kind of ad hoc business logic being constructed, transferred to executor nodes, and then being executed there, probably this approach would solve it right away. You're just building already serializable structure. So yeah, in order to explain that to others, probably you want to start from basic things: what a monad are, why do we need them, as a way to control the sequence of operations. Then explain why DSL matter. Well, that's the same thing I'm doing right now. So you have this possibility to separate the building of logic and interpreting. interpreting the logic, and then you should, well, describe why this approach is good. Okay. Okay. So I need to jump into another call. Okay. Thank you for attendance. Let us continue. Thank you. Let us continue. Probably I will jump into chat. So what do we have here? Repeat the question. Yeah. So probably there's no active questions. Okay. Next thing, we will have a break. I suggest something like 15 minutes. You can just take a deep breath and prepare for the next session. It would be shorter. I hope that we will take no longer than 1 hour to cover the Tagless Final and to wrap up. Thank you. I'm switching to timer. I'll see you in 15 minutes. Okay, so getting back to the presentation. So hi guys. We are returning from break. Let's quickly take a look at the chat. Sorry, I forgot to unmute my camera. So in chat, there's no new questions. Okay, so let us continue with the presentation. Okay, so the next section would be Tagless Final. Tagless Final is another approach of encoding our DSLs in a way that could be separated from actual interpretation. So first of all, let's talk about differences between tagged and tagless encodings. The first one, which we saw using Free-monads, could be considered as a tagged encoding because each operation was associated with a class, which could be considered as some kind of tagging the values with a tag. So the class was our tag. And in tagless encoding, we won't be wrapping our values into some kind of container. We won't be tagging. That's why this encoding is called tagless. Finally, let's take a look at what does the word final means. There's two encodings, initial and final. Initial encoding describes an entity by the way it's constructed, and final encoding describes an entity by the way how it's eliminated or deconstructed or viewed. For example, in Free-monads, we were creating an entity, for example, key value get, by constructing a class. So an entity was defined by the constructor, and in tagless, in pure final encoding, we would define an entity by its elimination, by its consumption. But to be more specific, that tagless final approach that I will be describing you today is basically tagless initial. So the name tagless final is more like historical, because pure final encoding is not very convenient in in TypeScript at least. So let's dive into the code. Oh, sorry. So in code, tagless final will be described in the folder called tagless final, which is located in the folder workshop. We will be using exactly the same API as in Free-monads, but we'll be using different encodings, so you can see how they compare to each other. So in order to describe an API in tagless final style, we do this. We define, let's describe the key value storage. We define an interface. I will call it KB store. That interface would have all those methods just as they are, similar to how they are described here. So kbget is a method which takes key as a string and returns, and here we will use that type kind, which I described earlier when I was talking about free monads and hierarchical types. And that kind will be abstracted by some type f, and it will hold an option of string. So again, I need to import an option module, pts with option, import option equals all.option. And I need to have that f type, and that type would be a type parameter to that interface f, and in order to be able to use it with kind, I need to say that f extends URIs. URIs. They are taken from FPTS with HKT as well, and this type represents all possible URI of type constructor with one argument. So the next one would be operation kv put. It has a key of type string, value of type string, and returns kind f boolean. And the last one would be kv delete. It accepts key of type string and return kind f of boolean as well. Read only. And I just export that interface. And that's all what it takes to describe an API in Tagless Final style. So basically what you're saying is that your API is polymorphic in type of container which will hold your return types. So you can, just the same as in free monads, you can plug in tests some synchronous container, and in tests I used again state, and in production you can use task or task either or something like that and plug that in, and you won't be needing to rewrite your business logic. But let's not let's take it sequentially. So the next interface would be database. Again, it would be polymorphic in type of container f. It has three operations: get posts. It takes user ID of type number and return. And again, here it should be option of DB post array. So it returns kind f option of DB post array, and I need to add DB post to my domain imports. Next one operation is create post. Read-only create post. Takes a post of type post, return kind f db post, and finally update post. Takes post ID of type number, update of type post update, and returns kind f option of db post. Yeah, that's it. Finally, this third one interface is a net sound fx in interface net sound f extends uis read-only net send is a polymorphic int function which takes a payload of type t, email of type string, and returns kind f void. So as you can see in tagless encoding, tagless final encoding, it's easier to express polymorphic functions. So if you need to write to describe an operation which has several type parameters. In Free-monads, you need to add all those type parameters to a class definition, and here you can just keep them at the point of declaration. Finally, we describe a type called program. F extends URI-S, and this will be an intersection of our KV store, database, net send, and in order to use the monadic behavior of this type, I will add an interface called Monad1 from FPTS. It's imported from FPTS with Monad. And that's all I need to do to express this API which I'm building in Tagless Final style. The benefit of Tagless Final is that in each method you can summon only those parts of functionality you need to in order to get the job done. So, for example, in cache get posts method, I don't need this whole program. I don't need network, I don't need database, I need just that interface KV store. And I will write exactly that. I'll say that F extends URI-S. I need KV is a KV store of F. So when I'm describing my public API in Tagless Final style, I make it a carried function with first parameter of type of those capabilities I require in order to execute that method. So you can, if it would be easier to you, you can think this style as of some kind of ad hoc dependency injection. So you are abstracting those that functionality, including the monadic functionality, to a parameter which will come first. In languages like Scala or Haskell, where there is a possibility to pass arguments implicitly. In Scala they are called, well, actually implicits. In Haskell they are called type classes. You can use that mechanisms to hide that passing of these arguments and make your APIs really neat. In TypeScript, we don't have any mechanism in implicit arguments passing, so we just write them explicitly, and I prefer to put them first, so your usage of your API would be straightforward and consistent. Okay, so in order to implement that, I need to call kv.kvget. I'm passing user ID stringified, and I get option of string, but I want really option of db post array, just the same as I want in Free-monadic API. So I need to transform that thing. I need to transform option of string into option of db post array, and in order to do that I need to take a look inside that kind f. So I need to extract somehow that option from that unknown container, and I could do that by requesting this kv to be a functor. This is done like this. I request this variable, this parameter, to be not only of interface kv store, but also of interface functor1, again taken from FPTS with functor1 of f. And now I can say that I can use kv map. As you can see, because it's now also a functor, I have this map method, which can take that arguments of kvget and transform option of string into something else. And because option is a functor, I will use that module option.map. Now I can transform my string into db post array by code json.parse str as db post array, and close the bracket. So yeah, now my cache get posts is a function which requires kv store and functor, takes user ID of type number and return kind f option of here the db post array is written actually just like that. The same goes for cache store posts, but here we won't need functor because we won't be translating those the results into something else. So I just need kv store. Oh, sorry, kv store of f, and here I can say kv put. String would be user ID, value would be JSON stringify my posts. And the result is already kind f of boolean, and that's perfectly fine, that's what I want. So the same I need in order to write my cache invalidation method. kv is a kv store of f, kv delete, user ID, and that's all, I guess. With the database we do the same. We need db as a database of f. I like to call those parameters in uppercase just to distinguish them from the normal parameters of my functions. So I call it kv in uppercase and db in uppercase. So db get posts by user ID. The same exactly logic would be here in create post. I'm just passing arguments as is. The same would be for updating the post, db update post by post ID and update. Of course, I can just use the eta elimination principle and get rid of those arguments and just write it like this. But I like to keep it explicit because probably I'd add some kind of documentation here, so I'd like to describe it more precisely. And finally, for the network, I need just net as net send of f, and I'm calling net send posts to. Yeah, and that's all you need to do in order to describe your API in Tagless Final style. One more thing. I like to make this helper function called getInstance4, where p would be my program of f, and I need to abstract by that fx. Oh gosh. Extends uris, and there I can just do the following. I'm creating a partially applied synonym to function, so I call a method on that object cache get posts. It would be cache get posts from P. And so on for the rest of the methods. Okay, let's do that. Cache store posts. This allows me to make my API a little bit simpler to use if you just want to import that API and work for that one particular interpreter, and that's all. Usage of those separate functions allows you to fully utilize the potential of Tagless Final style by requesting only that set of functionality which you require, but using this approach with getInstance4, you can just make your API straightforward. You call api.getInstance4 task interpreter, for example, and then you use that returned variable of that type as your actual API. db get posts, db get posts of p, db create post, db create posts of p, db update, and finally net send. So this is not something which is a part of actual Tagless Final encoding. That's just a pattern which I personally like to follow if I'm designing an API like that. So probably you can try that if you like. You can use it too. So yeah, that's concludes the describing of our API in Tagless Final style. If you haven't catch up yet, you can just check out the branch 04 Tagless API, which has this example of implementation in it. Now let's put that API to use and write an example. Import API from API. Okay, so I will add those imports which will be required for the job fpts contrib lib do. I will need a do notation. I will probably need option, fpts wave option. I will need pipe from pipeable. Yeah. So we are ready to write our example program. This program will work with cache, with the database and network, so it will require all the capabilities of the program. So we will just require the whole api.program of f. Yeah, okay, it checks. And in order to begin working with do notation, we need to pass an instance of our concrete monad, and that monad is available here in api.program. So we just pass that p, and we begin our work as in previous example. We start with cached posts, which are just API cache get posts from p from user ID. Then we get posts which we will be looking inside those cache posts, and then taking the same route as in Free-monads. If there's no posts in cache, we will get to the database and cache the posts. Otherwise, we will just return them. So cached posts option.fold. It takes 2 callbacks. Here I have posts. I need to wrap those posts into a monad, and I have that monad in my variable p in my program, so I just p off. Right, I will write p off posts, and finally here I need to chain calls of API.db get posts by user ID. Here I have posts p.map because I will need to transform the results of this call cache stored posts of p user ID posts, and then I will transform boolean to posts. Yeah. Okay. So I guess that's it. Finally, I can write bind L. Net and network would be just take those posts and call API.net send posts p posts review at example.com, and finally I'll do return. I return that net, and that net I will take from here. Okay. So f never is not assignable to kind type f of unknown. But what happens here? What did I forgot? Did I forgot something? Probably not. Okay. Cache post fold. Chain the biggest posts. That's really strange. What did I... okay, if I do here elimination, no. So I need that to be this kind, yeah, that's correct. And it infers that type correctly. Oh, yeah, that should work. Okay, I restart TypeScript? No. Something cryptic happens here, so oh, sorry. Okay, I guess that now doubling of my voice won't happen again. So thank you guys. Okay, let's get back to this thing. Program map, I required it to be a monad, yeah. That's correct. Database net send, everything's okay. Yes. And it worked for cache get posts, that's okay. And here it just I'm missing something, but I don't know what. It looks like I'm writing everything correctly, but it doesn't think so. Okay, if I write here just API dot db get posts of p of something, it will work. Okay, that's strange, because pipe should pipe that those that's option, yeah, that's okay. Option fault. Okay, if I don't write chain here, once again, db get posts of p of user ID. Okay, that compiles. Posts I need to return kind f of unknown. I have a functor of that. I have API cache store. Cache store posts of p user ID posts, and I need to transform that boolean into a post array, like that. It still doesn't accept that. What am I missing? Okay, maybe I missed something here. Okay, let me just check the reference implementation. I just have 3 interfaces and a monad. Okay, that checks. I just have that returns kind of option db posts. Okay, db get posts is just db get posts. That's okay too. That's rather unfortunate. I thought it wouldn't do that. Why does it think the return type is never? Okay, if I specify type in functor specify type cannot specify that explicitly. Cache store posts returns me a boolean. Those oh, wait a second. Oh, gosh. Those posts are option of db posts, and yeah, I understand. db get posts gets me an option. I don't need to map my functor. I need to why does it return me an option of? Yeah, because it returns an option in Free-monadic. That's okay. So in order to do that, I need to I need here to have posts. So here I will do just option dot pipe posts option dot map and here I have posts. Let's call that posts O, and here I have posts which I finally can store in my cache. And now I have an option of db post. That's something I don't want. Did we have this in Free-monads? db get posts. Oh, and then it had just an array and not an option. I'm sorry, I just implemented the method not the way I intended it to be implemented. So it's described like that. Option I have only in update. So now I can write it like that and then compile. Sorry. So yeah, there you have it. Program described in Tagless Final style. You abstract those capabilities, including the monadic behavior, in a parameter, and you use that parameter to access that behavior and pass it to your API, fulfilling those capabilities which your API requires. Again, I suggest you to implement the second and third example by yourself, and if you don't want to do that, please take the branch 05 tagless examples, which have them implemented. And now let's write interpreters. So what are interpreters in Tagless Final style? So I will have just the same interpreter, which will be interpreting my Tagless Final program into a task. And this thing would return me just program from my API of t.uri, which represents that fact that this interpreter would pass a task as a target for my program. Again, I will copy the fake cache and database from free-monadic interpreters, so I won't write them manually. I will import the db from utils.db. I will import John and his cool post from my domain logic. And finally, I can return a function. Not a function. I'm returning an object. This object should correspond to the interface program which I'm describing, and it has monadic behavior and a set of functions. So the monadic behavior I will take from monadic instance of task. And finally, I can write my implementation of my methods. So get posts by user ID. This would be t of. I need to have db post array, and again I need to import an option from fpts lib option. Option from nullable db fake no, not db fake object And why do I have here option if I have just db post array here? Object values, I'm sorry. Those values are taken from db fake by user ID. Next one is, just a second, why did I start with get posts? I should start with key value. It's simpler. Key we get by key. It should return what? It should return me a task of option of string. So t of option from nullable cache get by key. Okay. K we put it has a key and a value and returns t of, I need to have boolean cache set key value not equal to null. Kv delete is a function of key returns t of cache delete by key. Now the database, this is okay. Create post is a function which takes a post. It will create an ID for that post. Get next ID is imported from utils.db. For db fake by post author ID, const new post would be a spread of post and that ID. db fake by post author ID, ensuring that it exists, and then I will just write it in the database, and then I return t of new post. Okay, finally update post is a function which takes post ID and update. Does this existing post is to be fake by update author ID and by post ID. I will wrap it in option from nullable. Okay, I can return it actually. I can pipe that. And then I can call option.fault. If I don't have anything, I just return t of option none. If I have existing post, I will do this logic. I call updated post as a spread of existing post and update. I'm writing that to my database. Update author ID by post ID. I have it in scope. Is updated post, and then I return t of option sum updated post. Yeah, that will do. So I don't need a function here, just returning it like so. And the final one is netSend, is a function polymorphic and payload and has some email, and it just does nothing. So I will just ignore that payload and that email. So yeah, there you have it, an interpreter from in style of Tagless Final for program into task. And as I did with the Free-monads, in order for you to see how it's running in the runtime, I will create another thing called logger, and the logger would just transform an interpreter, task interpreter, into another interpreter, and it will do it like this. Unfortunately, here I need to write some boilerplate. I can't write that logger just as easily and in a nice manner as I did with Free-monads, because I need to override each method. Of course, I could just return to some unsafe JavaScript and call, I don't know, object values, object keys, and traverse it and construct some ad hoc object, but I want this to be type safe, so I will write that manually. So get is just this method, which we'll call console.log. It will be logging the name of operation get, and then JSON stringify key, and it will return task I get of key. So I need to write this implementation for each method I want to have logging. So yeah, a little bit of typing required. Okay, we put key value, console log. Okay, we put JSON stringify key value. I'm wrapping those arguments in an object, so the output of this logger would be exactly the same as output of the logger in Free-monad style, so you can compare those two outputs and see that they are literally letter by letter the same. Okay, we do it. Key return task interpreter. Okay, we do it by key console log do it JSON stringify key. Okay, get posts by user ID, task I get posts by user ID, console log get posts, JSON stringify user ID. Okay, create post, return task I, create post by post, console log post, JSON stringify that post, update and network. Okay. And console.log. And finally network. Payload email. Key not send. Payload email and console.log net send. JSON stringify payload email. Yeah. Okay, so this is the logger, which will transform a task interpreter into another interpreter which has each method logged. And finally, let's run those two examples. I will need, first of all, I will need that example 1 program. Then I will need my interpreters. I need task, get task interpreter, I need my logger. Yeah, so my task I would be get task interpreter. My interpreter final would be logger of task interpreter. And finally, I can call example program 1. I need to have this something is my interpreter. User ID would be john.id. And I have a task. I need to call the task to turn the task into a promise. So I'm just calling it. And finally, I can comment out that and remove not used. And here I can not implemented remove too. Okay, so finally let's run npm run colon tf to run the Tagless Final program. And you see the results are the same as they were if we ran our free-monadic example. So we go to cache, we didn't find anything there, so we go to database, then we store that in cache, then we send them over the network, and in second run we just go to cache, find those posts and send them to network. Just the same, almost letter by letter behavior which we had in free-monadic example. And again, you can always sprinkle this with task delay to see those delayed calls, so you know that it's running asynchronously. The results of implementing Tagless Final interpreters are available in a branch 06 Tagless interpreters. So if you want to take a look at the final result of this whole exercise during this workshop, you can just check out that branch. And again, there's a test for Tagless Final. Two tests are not compiling correctly because I don't have those programs. But I have my interpreter for state, which is running synchronously, just the same as with free monads. And actually the logic is really close. I'm just using state monad to do this. And I'm just in my tests, I'm running some initial state, and then I'm introspecting that state. For example, here's for second example where we create post. My initial state has an empty database, and after that example was executed, my next state would contain John ID and his cool post in it. So yeah, again, my tests are pure, my tests are synchronous, and in production I'm running some async computations. So yeah, there you have it. Two examples of building embedded eDSLs and free monads and in Tagless Final approach. From my perspective, explaining Tagless Final approach to others is is really simpler than explaining Free-monads, because Tagless Final is just an abstraction over the concrete container of effect which will be interpreted in. And this concept is really easy to grasp. You just know that, okay, I'm abstracting that, I will know how it will run later, and that's all. In Free-monads you need to know some really complicated stuff, but the Tagless Final has some drawbacks, as well as Free-monads have their drawbacks, and we will compare those two approaches later in the presentation. For now, I would like to compare two examples. So I have, I'll split my view. So take a look, please, how we implemented that example. If you squint a little, you can see that usage of our Free-monadic API and usage of our Tagless API is basically the same. You just need to carry that parameter of type P throughout the usage of API, and if you use that pattern that I showed, which is called get instance for, you get rid of that P, because you have it like so, const API API get instance for, and here you should pass your interpreter, which is basically this. So if you have that task interpreter, you can pass it here. And here you will just use that new API. But the logic is really the same. You're just working in some monad. You don't know which this monad would be, because free is, although it is a monad itself, but you don't know which concrete monad it would be in runtime, and the same goes for Tagless Final. So you just abstract in that sequence of actions away. You just use do notation or just directly chain in the method calls, and that's all. You're building you're expressing your business logic in some abstract way, which are then interpreted afterwards. Well, to be honest, not exactly afterwards. In Free-monads, the interpretation is strictly separated from the building of this abstract syntax tree. In Tagless Final, we do not build syntax tree. We just make immediate call, but due to the way how these APIs and their usage is constructed, we can make those calls delayed. Does anybody have a question about Tagless Final, or I can switch to comparison. Okay. In chat we don't have. Yeah. Okay. Voices out, but I fixed that. Sorry, there's some connection issues. Could you please repeat that, or maybe type in chat? I will say it loud. Okay, just a moment. I'll write in chat that. Okay, so I guess I can answer that later, and I will switch to my presentation. So let's compare both approaches, Tagless Final and Free-monads. In Free-monads, your program is data because you are building an abstract syntax tree. In Tagless Final, your program is an expression because you are basically abstracting those runtime capabilities from your business logic. In Free-monads, your programs are built from constructors, which are algebraic data types, which are basically containers which encode your actions. And in Tagless Final, your programs are built from API functions. So you have exactly the same type of action executed as you run. In Free-monads, your values are just values, just containers, just classes. In Tagless Final, you're dealing with expressions. They are abstracted by some kind of type constructor. In Free-monads, your values represent the abstract syntax of a program, and in Tagless Final, your expressions are just abstracted calls to the particular monad, actually. In Free-monads, as I told, interpretation is deferred, and in Tagless Final, the interpretation happens right when you call that expression. So when you write your program in Tagless Final style, you know that when you make a function call, it actually will be called when you supply that interpreter. Free-monads are stack safe, but with a twist, because actually it's quite easy to make a stack overflow in Free-monads if you do recurring calls, if you construct some kind of infinite loop. But you can really easily mitigate this by using trampoline technique. If you happen to read my Monadic Monday series, which I did in Twitter, I was talking about that, how to do trampoline with Free-monads. And in Tagless Final, your stack safety really depends on your monad, which you will be using for runtime. Again, in Free-monads, each operation is a value, represented as a value. Yeah, you just create an instance of a class in memory, and that's all. There's no execution. And in Tagless Final, you don't create those objects. You don't have those extra allocations. So you just have plain function calls. Free-monads, as I told earlier, could be quite easily introspected by actually pattern matching on that expression tree. And in Tagless Final, that's really hard because you have not an abstract syntax tree, but concrete execution stacks, so that would be hard. In Free-monads, you really require some boilerplate to combine languages, so to combine parts of your DSL. For example, if you wanted to extend your Free-monadic DSL with, I don't know, maybe a method to get a post by its ID, you will need to rewrite the interpreter, you will need to add that extra type, and so on. In Tagless Final, you can quite easily combine those languages, but you will have a harder time with combining interpreters for that, for those languages, which is the last part. So in Free-monads, it's easy to extend language, and it's harder to extend an interpreter. And in Tagless Final, it's vice versa. Yeah, okay, so we have a question. John Goes in Twitter said a prediction that Tagless Final, while still useful to high-scaled, high-discipline teams to embed call graph documentation into types, imposes such significant costs and for so little practical gain, no amount of education can reverse current trend lines. Although I deeply respect John for what he's doing, his takes on Tagless Final should really be taken with a grain of salt, because you should understand that John right now really aggressively marketing his Zio. Zio is awesome library, hands down. I've used it. It's just incredible. It's very ergonomic. It's very performant. It has rich IDE support. For example, there's a plugin for IntelliJ IDEA to support Zio-specific refactorings and linting, and it's brilliant. But in order to sell Zio, John needs to, well, actually trash Tagless Final, trash Free-monads, and well, sell Zio. I would agree that his approach it feels more idiomatic for Scala, feels more easily to be explained and taught to others. In TypeScript, unfortunately, we don't have native good capabilities of working with monads, so we don't have any native-like way of doing these things. So I'd say that both approaches which I described to you today are quite hard. Hard to teach, hard to explain. They do require some boilerplate in TypeScript, but that boilerplate could, for example, be mitigated by using code generation tools. For example, you can generate your tagless API from, I don't know, from OpenAPI specification, for example. Yeah, so that's and the second question: how does Tagless Final approach connect to an effect system like Monads effect based on PTS? The things like Monads effect or QIO are how should I express that? Are ports of Zio to TypeScript, to be honest. So they all are concrete monads, so you don't get that abstraction. For example, if you use Monads effects, or, well, okay, if you use Zio, let's talk it like that. If you use Zio to express your programs, your tests also will be asynchronous, because Zio is asynchronous, and if you're using TypeScript Monads effect, you will be writing your code in that. If I remember correctly, before Monads effect, there was a library called waveguide. So if you're using that, your concrete effect will always be that type, wave or QIO or Monads or something like that. So you're losing that capability of running tests synchronously and in production run asynchronously. You're losing the whole capability of translating your programs into different monads. That's a tricky question, whether you really need that. With Free-monads, I have this one really good example, which I described when you need to serialize your logic, pass it to executor node, and deserialize and run it there. So that's a way which will require much more efforts in any concrete effect systems. But from if we are talking from the point of ergonomics and let me say teachability, then of course concrete effects are much easier to grasp. So yeah, that's it. That's my thought on that matter. I hope I answered your questions. Okay, yeah, fine. Finally, I can answer some other questions. That's all for this workshop. I thank you all for being with me. I thank those who were with me on call. I thank those who were in live chat, and of course, I thank those who will watch this in recording. I can answer some questions about the topic, or if there's no question, I can just wrap up and finish this workshop. Okay, so I see there's no new questions. Thank you very much. Thank you for being with me. And I guess I'll see you next time. Keep watching. Subscribe to Rainy. It's a really cool initiative to make an open source education. So subscribe. Put your likes, put your comments, and cheers. See you later.